9 is 3, then 4. And we divide this, we got minus 1.5. So now that means our t value, the t value that we calculated is minus 1.5. Now, the critical value that we check on the table is minus 1.860. Now, now let me show you what this, there will be a special video for critical value on its own, but let me just show you what that means so that you understand it more. Look at it now. In this case, what critical value means is that, look at this table. Now I told you that we can set range from year to year is 100%. So if I am testing, if my hypothesis testing is 95%, that means it will be from year to year. Now, what this critical value simply means is that any other value that goes outside here will be rejected, but the one that fall within here will be accepted. That's the meaning of critical. So this point and this point on both sides is the critical value. So what we saw in our calculation is that when we check our critical value from table, we have minus 1.860. Now when we calculate, we got minus 1.5. You agree with me that it is within the range. So that means we will not reject the hypothesis. That shows that that mean is still allowable. The mean that we calculate 118 at 5% significant level is still allowable. So this is what it is all about. So the chi-square, I told you, in this chi-square, you are still, look at it, for chi-square, this is how you understand chi-square. You are still considering a single population, just like this, single population. And you are comparing your population with the sample. This is the population, this is the sample. So you're comparing it together, that is chi-square. So that means in this case now we have the sample variance, you have the sample variance, you have the population variance, and you have the number of values. So now this one also have degree of freedom. We're going to be checking how to evaluate this on the table later. So this is the question. A machine is designed to produce an item with a variance of 4 mm square. Look at it now. So that means generally the entire population of the machine that was designed was 4 mm. So we can call that population variance. That's why population variance here is 4. Now a quality inspector now comes and selects a sample from it and found out that the variance of that sample is cm, that's x squared, that's 6 mm. Now you now see we should test it. You understand? Don't forget, in this case, there's a mistake. He selected 15 items. It was not well shown. He selected 15 items. That means the number of n will be 15. Degree of freedom will be n minus 1, which is 14. So now, in this case, we're going to compute the chi-square. And just like I said that time, don't forget, all we are trying to do now is just to compare critical value. If we have this, if this range is our critical value, anything we're going to be calculating, before we can accept it, it must be within here. If it's outside, we will reject. If it's within, we will accept. So critical value is just like the boundary point. So now let's go back. What we are calculating now is the chi-square. So we put 14, which is n minus 1, then 6, which is the sample variance, all over population variance, that's 84. So 21, that's the chi-square value. Now when we go to the chi-square table and we now check, degree of freedom is n minus 1, which is 14, and this. So you see this degree of freedom and the significant level. Let me, before I bring the table so that you understand what we are doing, it's just like the table is like this. That's row, it has column. So the degree of freedom will be down here and the significant level will be here. So for instance, in that our question now, you will check 5% here and you will check 14 here. So anywhere they meet, that's the value you are going to pick. So when they did that, the value they got was 23. So that shows that what this implies is that here is 23 on the positive side now. And when they now calculated, the calculated value was 21. So it shows that you agree with me that 21 will be within. So that means we will not reject, we will accept it. So in this case, there is enough evidence to say that the variance, so we will fail to reject it. Now let's move on. When you're comparing two variances from two different samples now, you understand? Two different samples. Like I told you, this is the foundation for ANOVA. And the reason why ANOVA is a little bit more complex than this is that ANOVA is like, in this case, we only compare two together. In ANOVA, you can compare 3, 4, 5, 6 together. So for F distribution, we're comparing two samples. Now, what does this mean now? Let me come back to our diagram. What it means is that, this is the entire population. There is a sample here and another sample here. So in this case now, we are comparing this sample and this sample. This sample and this sample. From the same entire population, this sample and this sample. So that is F distribution. So here, we'll come back here. We'll see this just for F distribution, its own degree of freedom are always two values. The n-1 for the first distribution and the n-1 for the second distribution. So now let's go back here. In this problem, we have two machines produce both. So machine A has the variance 5, sample size 10. Machine B has the variance 3, sample size 12. So we have to test at 5 significant level if the two machines have. So we're going to see in this case, since we are comparing two variants together, sample variance, we're going to be using the F distribution. So the sample variance for the first one is 5, we'll put 5. Second one is 3, we'll go to 1.67. So now F value for 2 degree of freedom. You see the difference between degree of freedom for F and other ones is that on the table for F distribution, we're going to be having, look at it, we have the first degree of freedom, we have the second degree of freedom. So let's say we are comparing, let's look at our question here. We're comparing 11 because that's n-1, 9 and 11 together. So we'll check where 9 is here and we'll check where the 11, wherever they meet, that is where we're going to be checking. So F distribution is such that a single table like this will be for 5%, another table will be for 10%. So that's how you are going to be checking it. So now when we calculated, we got 1.67. When we check the table, we got 3.29. So what that implies is that, look at it, this range here is 3.29 and the calculated value here is 1.67. So you can agree with me that it is still within that range. So we are going to reject we will not reject the null hypothesis. We're going to accept it. There's no significant difference. So, and like I said that time, this is just a section that explains the confidence interval more for you. So what this formula does is that, the boundary I talked about. You remember I talked about a boundary here, that boundary is just like what we're going to be needing, what we will need before we can know whether to reject or accept any of those stuff. So this confidence interval, now look at it. Now if you have a normal distribution like this, look at it. So confidence interval is what will let you know, okay, from here, look at it, from here to here, anything within this region is what we're going to be accepting. Anything outside it, we will reject it. Do you understand? So this is what this confidence interval is all about. So what you just see here are the possible formulas for calculating confidence interval using different things. So this first one now, most time is very on a very ideal situation. This section is not always very disturbing like that. That is, when I say very disturbing, you may not lay too much emphasis on this, but it's good to understand it. It's always good to understand it. So when your completion variance is no, or standard deviation is no, this is what you do. When it is unknown, you know that's the t-test. That's what you do. So this is just a summary of the confidence interval for various cases. So when you have your population standard deviation known, you will use this. When you don't know standard deviation, you use t-test. So when you have two mean, you understand, and it is t-z, this is how you do it. When you have two mean and it is t, this is how you do it. You understand? So, and this is what we call the proof sample. I will do a separate video on this confidence interval because of our time. Let's just take a sample of 50 students has an average test score of 78. Now don't forget, once you see 50 students, that means the n is greater than 30. It is Z distribution, so we'll not disturb ourselves. Has an average score of 70, that means the mean sample mean is 78. The standard deviation is 10. Now at 95 confidence interval, so on the Z table, you can always check for confidence interval of 95%. You will get 1.96. You understand? So if you want to know our confidence interval now, we're going to come to this formula. What you see here in this step 2 is just them breaking this formula into 2. You understand? That is what they call margin of error. Is just from this Z alpha over 2 and then deviation over this. So this part alone is what they calculated alone here. So they calculated that part alone in this place. So the Z alpha over 2 for 95 confidence interval is 1.96. The separation standard deviation is 10. So we have this, and the number of samples is 50. So we have this. So we get 2.77. So now, and since the mean is 17, you see now that this thing is creating like a range. So it will be less or greater. So we will add and subtract. 78 we subtract 2. 78 we add 2. So within this range now, any mean or any average that fall within this range will be accepted. So generally, hypothesis testing is another important part. We have been doing it since we started doing it, but it's just for you to understand it. So there are like many things you need to understand about hypothesis. The first, the null hypothesis. That is the present condition that you set your research or observation to. So the alternative now is the claim that is different. For instance now, if you say the manufacturer's error for an instrument, maybe when they will build the instrument, they said, okay, the error in this instrument is just within 2 mm. So now, if that's what the company says, you understand? So now we are now using the instrument, then we now discover 2.1 or 2.2 mm. So we can now set an hypothesis and say, okay, there is no difference between 2 mm and 2.1 mm. That is, there's no significant difference. That's our null hypothesis. You understand? So our alternative hypothesis now will now be, oh, there is difference. So there is difference. So then that is the H1. So now, while you are doing this, you can commit 2 types of error. Number one error is that when your hypothesis is true, that is, it is really true that there is no difference between 2.0 and 2.1, then you now go and reject it. That's you have committed a type 1 error. You understand? So, or when there is a huge difference and you accept it, that is type 2 error. You understand? So, and under the hypothesis testing, we have 1 tail test and 2 tail test. It's just like what we have. The 1 tail and 2 tail test is better described when you are attacking the test from both sides. Look at it now. You will notice that our observation here has 2 sides. This is side 1 and this side 2. So if you are only focusing on this side during your test, that's 1 tail test, or this side during your test, one. But if you are attacking it from both sides, that's more or less like a 2 tail test. It's just a very simple analogy of the whole thing. So this is a simple test, a simple approach for all the type of tests. You are going to, number 1, you state the purpose while you are doing the test. Number 2, okay, this is just a summary of it. Let me see if you can. So these are the key things you need to examine. Number 1, you state the purpose of your test. You set your null hypothesis. Then you tell us your significance level. You carry out the test statistics. Either it is Z. If it is Z, you do Z. If it is T, you do T. If it is chi, you do chi. If it is F, you do F test. Then after that, you compare it. Then if it is something you need to reject, you reject. If it's something you need to accept, you accept. Then you draw your conclusion and say, okay, this is this. So that is just, by the way, other videos we're still going to be going more deep. These are just the summary of the things we have done.